I want to get this event started, formally get this going. For this going to be a fantastic 12-week series teaching you about Filecoin, teaching you about the whole protocol labs, ecosystem, and everything in between. We really have some phenomenal events planned, not just over the next 12 weeks or so, but going into a hackathon, going into an accelerator. And I'm going to spend 5 to 10 minutes now just telling you about the program in general. And then we have Yiannis, who's going to give you the talks today and also talk to you about kind of the content that's coming up in the coming weeks. We've got a lot for you to learn today in this first event, which is kind of an introduction to Web3, which I will give you a foundation going into the next 12 weeks or so. This is the Encode Filecoin Club. It's a club. Everything in Encode is a club because we want it to be inclusive and fun and for you to be feel absolutely part of something. And this is constituent. This is kind of constituted of 3 main things. So, as I said, we are doing a 12-week education series every week. This time on a Tuesday, there is a new piece of content, a new event for you to kind of take part in and kind of learn about. This is completely open to anyone, but obviously it's aimed at the more kind of the person who wants to kind of really get involved in the Filecoin ecosystem, learn about what's to offer, learn some skills, and really go get stuck in to the ecosystem, and then leads in to our global Filecoin hackathon in October, which will last for 8 weeks for you to build hopefully your first project within the kind of broader Filecoin ecosystem. And for those of you that's going to be successful, which I hope many of you do, there might be some great startups that emerge. And certainly in the programs we've done with Filecoin before, we've seen some brilliant startups emerge that have gone to be extremely successful. And the accelerator is there for just that. There are many, many other opportunities, career opportunities, learning opportunities, ambassadorial opportunities for you to get involved in within the Encode Filecoin Club. And we hope to share those with you over the next, 9 months. Quick word about Encode. Encode, we are hosting this series in partnership, in collaboration with Filecoin and Protocol Labs. And the whole point of Encode is to bring new developer talents, new talent in general, into the blockchain space and really educate you and give you the tools you need to go on and get involved in the space and what is the perfect time to do so on the back of all the excitement and kind of market activity of the last kind of year or so. Now is the time to build, and there's so many people in the space, and I'm looking forward to seeing many of you go and do that. We do this by educating, supporting, and catalyzing, educating through events like today to talk to you about what is blockchain, how to get involved, what's actually happening there technically, supporting you through programs, hackathons for you to build projects, to kind of start building your skills, and hopefully catalyzing you to go on to get a job, to go on to build a company, go on to have just the skills to know what blockchain is and what particularly what Filecoin is in this series. We work primarily with the university community, but please, if you're not part of a university, that doesn't matter. Encode is open to everyone, but I know that we are joined by many developers and leads from student clubs and societies all around the world, and that is very pleasing to me. I think Encode is at the forefront in helping kind of university talent get into the space, and we'll continue doing that. So if you are part of the many universities following Encode, thank you for your continued support and work on the ground, and we're looking forward to seeing you take part in this program. And we've worked with lots of good companies, but there's only one company we care about today, which is Filecoin. In terms of the timeline overview, this series runs for 12 weeks. We then go to the hackathon in October, takes us into Christmas, God forbid, and then the accelerator in January, April. So it really is a long-term program, and we very much encourage you to take part as much as you can, but know this is a flexible structure. You can come in, you can come out, you can watch everything remotely or in your own time if you want to. The hackathon is a long structure, to allow you to build a better project, but also to allow you to do it at your own pace. We really want this to be, you should have no reason not to take part in this and make this as easy and flexible as possible for you to do so. I've talked about the 12 events. Yiannis will tell us more, but they are every Tuesday at 5:30, all happening online. Everything's recorded, uploaded with slides and course material alongside that, so that you can learn every Tuesday. This is the schedule. Yiannis will also tell us more about that, but just so you can see what kind of things we have in store, pretty much everything you could hope to kind of have within the kind of Filecoin ecosystem. And then we move into the hackathon, which is an 8-week global hackathon in October. Where you get to answer challenges, get prizes, and we'll run even more workshops going really into how to build kind of actual projects in the hackathon itself. This is the structure of hackathon. We can go into that at a later date. And the accelerator, I'm pleased to say we've had so many startups come out of Encode recently and gone to be extremely successful. And the accelerator is part of that. And the idea is that once you finish the hackathon, or if you're just a researcher or an entrepreneurial person in general, that you can come into the accelerator and spend 10 weeks kind of trying on what it's like to run a startup, and hopefully at the end of it, raise funding, grant funding, code invest funding from our fund, money from Filecoin, money from VCs, etc., etc. And really, we think this sits in between kind of this kind of moment of takeoff, kind of going full time, quitting your job, perhaps quitting your studies to do this, but not necessarily, and it sits quite nicely there. And now I've kind of said my piece, and I want to introduce Yiannis, who's our speaker today, and will be kind of setting the tone. And I'm really pleased to say Yiannis is actually, albeit a few years ago, has taken part in one of our programs before. So he really knows what it's like to be on kind of your side. And on top of that, he is a phenomenal researcher, particularly kind of in the world of kind of edge computing, and has joined Protocol Labs to kind of real huge part of their efforts and continued efforts to not just have the best technology in the space, but further it. And he was a researcher at UCL for 10 years. So yes, I'm so pleased to have you here. Over to you. I've set the tone for just what we can expect, but the real good bit of today is hearing you speak. So thank you so much for joining us, and I'm really looking forward to your talk. So over to you.
Thank you. Thank you so much, everyone, for joining. And thank you, Anthony, for the great, first of all, great initiative, to be honest. What you're doing with Encode Club seems really, really different to what I've seen before, and really like setting teams and people for success. So that's really great. I'm looking forward to the rest of the event. I'm going to follow it up myself, actually. The whole program looks so interesting. So hello everyone, and it's so nice to be here. I will start, as Anthony said, by going a little bit into what is going to look like in the coming weeks from the point of view of the sessions that you are going to have. So I hope you can see my screen. What we can do is, of course, feel free to ask questions. What we ideally should do is ask questions in the chat. Some of them might be answered along the way from other people joining here and knowing the answers, or from other people from Protocol Labs that are joining. Or otherwise, if they don't get answered, then of course, I'm more than happy to have, as long as you want, Q&A session after the end of the talks that we're going to have today. So we're going to start today in week 1 with a general introduction to Web3. What does it do? What does it stand for? The distributed web, as it's otherwise called. And then we're going to do a kind of deep dive into content addressing, which is a very, very critical part of what you're going to hear in the following weeks, because everything in the IPFS and Filecoin ecosystems is basically is based on content addressing. This is the very main basic principle. And then we're going to have a colleague of mine, Alfonso, who is going to talk about content routing. This is a very, again, of course, very central part to how you use IPFS, how you use Filecoin, and all the pieces behind it, you know, how content eventually comes to your computer. Then in week 2, we're going to have, like, the rest of the week, some of them, they're going to be presented by Protocol Labs engineers and researchers, but some of them, they're going to be ecosystem partners, like companies and other organizations that Protocol Labs is working with in order to make the Web3 a reality. So this is a huge privilege, because you're going to also hear about, you know, how it is like to use and what other people have done with IPFS and Filecoin, and hopefully this will give you more ideas so that you can go on to the hackathons and the accelerators and build your own stuff as well. So the second week is going to focus on how IPFS deals with files, and we're going to start actually putting already from the second week concepts like content addressing and content routing into the real world and how IPFS uses them. Then there is a series of intros, like kind of deep dives on P2P, the peer-to-peer, the network layer protocol and library for peer-to-peer networks that is underneath IPFS and underneath Filecoin. Then there is going to be an introduction to Filecoin itself, to IPLD as well. I'm going to briefly touch on IPLD today. IPLD is the interplanetary linked data. And it's the data model that is used by IPFS and Filecoin and the Web3 more generally. Another very central part, if you want to go into data structures and understand the, bits and pieces inside IPFS and Filecoin. Then we're going to go, the program is going to dive a little bit deeper into building stuff. So the 6th week is going to be on building applications with IPFS. And an introduction to NFTs, which is kind of, well, it's not a new thing, but there has been huge like uptake and usage from several different applications and uses around IPFS. So you're going to hear how non-fungible tokens can very easily be stored on IPFS. And from stats that I have been hearing recently, the majority of NFTs that exist in the world these days, they are stored on IPFS. So very, very to the point talk there. Then hosting with IPFS, if you want to host your website with IPFS, and how does it look and what do you do? And what are the pinning services, again, about hosting and storing files on IPFS. Very interesting talks there with lots of details on how you can use it, how you can extend those services. Then building with Filecoin, there is going to be another session on things that someone can actually do with Filecoin. And there are lots that can be done there with Filecoin and IPFS, of course, already. But there are many more that the potential under those platforms is just amazing. There is so much that can be done that there are more ideas and more effort here needed. Then week 11, it's going to be about storing data on the Filecoin network. And finally, week 12, how mining works on Filecoin. As you all know, Filecoin is a blockchain-based decentralized storage network that uses its own blockchain. And therefore, there are lots of things that, there are lots of details that go on in the background about how the blockchain, how miners join the network, how they contribute to the network by adding storage, and finally, how they extend the blockchain. How do you create blocks? What all these things mean in kind of Filecoin parlance, and how the whole system actually works. Very interesting. I'm sure you're going to appreciate it a lot. Now, with this, I would like to kind of make another introduction to extra material that exists and we have put together under the umbrella of ResNetLab. Now, ResNetLab is a research lab within Protocol Labs research, more in particular, and stands for Resilient Networks Lab. And what we do at ResNetLab is that we're trying to equip the projects, the Web3 ecosystem and the projects, IPFS, P2P, Filecoin, to be able to be resilient against all sorts of dynamicity in the system. So this could be resilience against attacks and malicious players in open source and permissionless systems, such as everything basically that is built under Web3, but also the dynamicity in terms of different load in the network. If there is a peak in workload, then the protocols and everything need to be prepared to deal with those. So what we have done is that we have put together a great video tutorial series, which we called ResNetLab on Tour, and there is this very nice bus, magic bus logo there. The first part of what I'm going to talk about today in the first module, which is not going to take more than 10-15 minutes, is going to be an introductory part to ResNetLab on tour, and also get an introduction to Web3 as promised. So the program, what is the ResNetLab on tour that we have put together? We wanted to create a bridge to decentralized web research. So we wanted to reach out to so many researchers, academics, postdoctoral researchers, and developers that want to actually put their knowledge and from their previous work into this vision of building the Web3. So we have invited the entire research community to think about the challenges that we have, because there are many. The space is very exciting, but it's got its own challenges. And all this group of people, researchers, academics, developers, they have huge experience from their past studies, which they contribute here. So what we did is that we went to all those events and we engaged with thousands of academics, thousands of researchers. Most of them, they are academic conferences, but some of them, they are also developer conferences and other events. And we have presented the whole of the stack, basically. And what we wanted to do is not only make it available to those that are participating in the conference, but also make it available async, and make it available not only to those that can travel in different some different circumstances and years to the conferences, but also to others. So we've created core modules and elective modules. So we split the content that we wanted into, and I'm going to paste the link to the website where you can find each one of those core and elective modules. They're about 20 to 30 minutes each. And we're adding more. The program has not finished yet, but there are the 5 core modules and another, I think, 3 elective modules that are live already. The core modules cover the welcome one that I'm going to do today. Then we have content addressing and content routing, and then the exchange of content, how content is actually shipped from one peer to the other, and how can one deal with mutable content. All these, needless to say, is open source, so we are going to share the slides that I'm presenting today and those of all the other modules. And we're more than happy for you to take and use those slides for your lectures, university events, conferences, or other meetups that you want to organize. There are links there. We can come and talk to your event as well. There are contact forms, and also a GitHub discussion repository where we can start the discussion there. Now, let's go to the main part of Web2, which is what we have today, and the challenges that it presents, and why we think that we need to make a step further and go to the Web3. Now, the Web2, what we have today is this great thing called the internet, and we have all those thousands of applications that we use for work, for personal reasons, for entertainment, to talk to friends and colleagues and loved ones. And there has been great value that we have all taken out of those applications. One of the problems with what we have today is pretty much none of these applications can work offline. And this is attributed basically to the main principle of how the web, the main internet, the protocol stack is working today. This is what we call location addressing, and it translates to the way that computers in the internet can get and serve requests from the users, from those applications or from your web browser. So what is happening is that we have those URLs, the example.com, and what the machinery in the internet, the DNS in particular, is generally translating the URLs to specific addresses, what we call IP address, and I'm sure every one of you knows that. Now, what we do with that is that we go and talk to that specific IP address, and we ask for the content, or we interact with the application. The problem is that if some part of the network becomes fragmented or goes down, like it could be a network router, it could be a link, it could be anything. We basically don't have access to this content, even if the content that we're asking for is already consumed and downloaded from other computers in the network. So the next step is that we say, okay, what do we need to do with that? Is we need to go to a different model, which is the content addressing model that I'm going to introduce in a bit. Another problem with what we have today, with the protocols and the protocol stack that we have today, is that it's not resource efficient. So if, imagine every one of us being in the same room in the same conference, if we wanted to stream a video or download the set of slides that I'm presenting, we would all go and make a request to the web browser and we would download the file. Now the file would actually travel through the network like hundreds of times or as many as we are here. This is not very efficient, obviously, and as we go to high definition, ultra high definition video and so on, you can imagine that the load that we're putting into the internet links is becoming very, very expensive for the network, very expensive for those that operate the networks and so on. And there are more kind of problems or challenges with what we have today, with the internet that we have today. The internet can be easily controlled. So sometimes, well, we have all seen, hopefully not experienced firsthand, but we have all seen that governments in some parts of the world can just cut the internet and not make available some specific website or access to the entire internet. So that's not very good, of course, for we want all to be able to learn more and get more educated through the internet. It doesn't work in disconnected environments, as I said. It's not very efficient in terms of bandwidth. And we hear security vulnerabilities that come out, especially as we go into the world of edge computing and Internet of Things, and so much of our lives is dependent on those issues. There are security issues that very greatly harm the applications that we're using. So here comes IPFS, the interplanetary file system, which is building a different infrastructure, a different platform where we can extend those applications. We don't need to migrate things into something new, but we can extend those applications and the protocols that we have to something much more efficient. It includes IPFS as a protocol stack, includes all the features that are needed in order for applications to work offline, to be safer, to permanently store copies of content that we don't want to get lost once a company, say, goes out of business, and also, of course, make it safer and faster. Now, in order to enable this, IPFS and Web3 more in general go from the location-based principle that the internet is operating under right now to what we call the content-based addressing. So we're not interested anymore into where the content lives, if it's under one specific IP address, but what we want to see is content being addressed by what is included inside the web page or the file, and therefore be addressed by that. And that's how the internet, like the rest of the network, should translate it. These are the two kind of different worlds that we're going to be diving into today. And it should be mentioned that there is a really big ecosystem of applications. This must be just a subset of it because it's growing by the week, of companies and groups and individuals that build on top of IPFS applications that take inspiration of what we use today and take it to the next level to work under this distributed web. So you can find decentralized YouTube-like applications. You can find decentralized audio and music streaming applications. There are lots of developer tools that someone can use in order to host websites and so on. IPFS is also integrated into browser. So if you're using Brave, you can access IPFS directly from the browser. You don't need to put the HTTP : / prefix there. You can just go directly and search for content hash, which is what I'm going to dive into in a little bit. There are also decentralized identity systems such as ION, and that's a very interesting project that takes the decentralized web to the next level by integrating identities as well. Very important, as we all can imagine. Now, all of those projects are open source. There are thousands of contributors, and you're very encouraged to get involved in the community. At ResNetLab and the research part, we do also have a research community there that if you fall on that side and you like researching new things and putting past knowledge into practice, then get in touch. Certainly, we do have a very large list of open problems, which I'm going to paste in the chat after the talk, so that you can get inspiration, see what are the burning problems there, and how you can contribute to help everyone. Now, getting into the Web3 now and what it is. So the internet, in the beginning there was a bunch of cables that was connecting universities. Then the next phase were all these, the wave of applications that we started seeing, like in around the 90s, let's say, maybe a bit before that, and certainly a little bit after, with applications like Google, Yahoo, MSN, and so on, that have been basically the read-only web, which there was no interaction there. You would go to a website and you would read information, you would consume information kind of passively. What we have today, which is Web 2, we have lots of interaction. We have all those applications, such as even the one that we are using right now, which can run on the web browser or as a standalone application. And we have interaction. You can interact with your bank, you can interact through a video conference, you can interact while playing games. Now, the Web 3, the next step, is a construction that takes lots of other pieces together and puts them in one package, so that we do this next step. It's the distributed web that I just introduced, which works offline. It's faster, it's safer, and it doesn't need to have a central point of coordination. It's open source and it's permissionless. Now, this is joined by blockchain, or distributed ledger technology, if you prefer this term, which is publicly verifiable data. Everything, as you know, that is stored on a blockchain is publicly verifiable data. It's permissionless, so anyone can join. There is no central authority that would do access control of any sort. And there is incentive alignment. So when in most of the applications and platforms that are built today under the kind of umbrella or concept of Web3, means that you contribute resources to the network, and then you get reward back for that. In the case of Filecoin, which is the topic of this whole program, you contribute storage capacity into the network in order for other users to come and store data on your machine. And then, as a miner, you contribute storage, you extend the blockchain by submitting all the information that is needed, proofs and things like that. You extend the blockchain, and then you win rewards according to your contribution. So the more storage you contribute to the network, the more you can have, the more you get as a return. And finally, there is the semantic web, so which is basically, you can see that as a graph of knowledge, where there need to be very strong data models underneath that. And in IPFS and Filecoin, this is done by IPLD, which is the data model of the web. And of course, by putting those things into a more concrete structure, you can have a programmable understanding of what the application does. So you can think of that as smart contracts, for example, that build on top of blockchains. Now, with that, there are many there are many features that come together with those three components that I just mentioned. They're all open source and publicly auditable, as you have seen in very many projects, I'm sure, through Encode, but not only, other projects in this space. These are forkable, so if you want to add a different feature, and like the rest of the community does not agree with that or does not want to support it as in the main kind of direction of the project, then you can fork it and start a new application or project based on the same principles. There is permissionless entry, as I said, so anyone can join and contribute to the network with storage, for example, in Filecoin, but with computation in other initiatives. There are programmable agreements, as I said, smart contract-like things. And there are crypto economics, a very central part. So, we go from the traditional economy to these crypto and token-based projects and protocols where the economics is a very central part. So there is lots of research going on there, and there are still many issues to be investigated. But it's a very exciting space. Now with this, where we go is that we have all this new booming ecosystem of projects that is not only an interactive web, but it's verifiable. You can publicly verify if the information that you're getting is the information you asked for. You can go and publicly verify on a blockchain if the information that you see that you have been given is correct or not, and so on. So it's the kind of trustless web from the point of view that you don't basically need to trust a single entity, a single company that is building some application, but you can actually verify it yourself. And here is just a sneak peek of all the different logos of companies that build on top of Web3 protocols, and they don't touch only on one kind of user application, but you can find lots of things, from technical things and developer tools. You can find financial applications that target financial use cases, to personal data, like to applications for personal use, such as data storage, as I said, and video and audio streaming. So with this, I will finish the kind of introductory tutorial. I hope it didn't take much longer than was needed. But yeah, we can pause here and get any questions. I should have mentioned I'm not seeing the chat in real time. I hope that the discussion goes on there in parallel, but that's a good time to raise any questions.
Awesome. Thank you very much, Yiannis. Should we take some of the questions? Shall I read them out?
This is a question for me. Yes, absolutely. I'm happy to get questions.
I think let's read a few. I'll pick out some of the best ones, and maybe I could read a few. So someone says, do you think long-term people will pay for storage the way they pay for data on their phones?
Oh, that's a great point. We actually had a research project in the past where we wrote a paper about that. Yes, I do believe that as we go towards kind of IoT and these kind of edge computing use cases where lots of data is kind of produced near where the user is from our devices and the smart devices, I believe that uploading these data is going to be still expensive, even with 5G and everything. So what you need there is a decentralized kind of storage infrastructure where you can dump your data, and this can be a kind of product like offering from ISPs and similar companies where, instead of having just download capacity, which is what we have today with, how many gigabytes per month you have and all that, this is going to become super cheap. But what you will need is the upload capacity and the storage capacity. This is what is going to be expensive for the network end to end. So yes, that's a very good point. I do believe that we are in the long term going to be paying for storage at the edge. Yeah.
Awesome. A more basic question here. What is the difference between Filecoin Protocol Labs and IPFS? I guess a better question is, how do they interact with each other as entities / protocols /
Yeah.
tokens.
Yeah, absolutely. Let's starting from the basic from Protocol Labs is a research and development organization that supports both IPFS and Filecoin and other projects. IPLD is another project, libp2p is another project. They all come together in a kind of protocol stack. So they're not like random pieces, they are pieces of the same puzzle. And Protocol Lab supports these, the development of those projects. However, it is very important to make clear that Protocol Labs is not behind, these are community projects. So the community is basically driving decisions around, such as, like, for example, the Filecoin improvement proposals, similar to Ethereum improvement proposals. There's discussion with the community, and whatever the community decides goes on. So although Protocol Labs is supporting those projects, it does not own in any way any of them.
Very good. Where do you see Filecoin in 5 years? Will it look like AWS?
I think it will, like, my personal opinion is that the foundations of the protocol and all the algorithms and mechanisms that are included there, they're really very well thought. And there has been huge effort by everyone involved, from the community, from Protocol Labs, from other companies. And I do believe that the foundations are there. So to make something very big happen. Now, yeah, I cannot make predictions whether it's going to look like AWS or not, but I can certainly say that my personal opinion is that the foundations are very strong, and therefore it's going to become the leading kind of storage protocol, in the decentralized web space.
Awesome. What research roles are available at Protocol Labs?
There are many. I can post a link, but there are research engineer positions, there are research scientist positions, and they're like in several different of the labs. Like ResNetLab is one of them. As I said, it kind of focuses more on the networks part of the whole stack, but there are other, like CryptoNetLab, which is about cryptographic protocols that support Filecoin. And not only, there's the crypto economics lab, which goes towards the economics behind token-based protocols. So yeah, check them out, and I'll post a link to all the open positions, but certainly there are many.
Awesome. How does mining work in Filecoin? This preempts a future lecture, but do you want to give a 30 seconds on mining?
Right. How does mining work on Filecoin? I certainly can. So when you join the Filecoin network as a miner, you onboard storage. So you buy hard disks, and you register them with the Filecoin network, with the blockchain. Now, every time from that point on, storage exists under your kind of Filecoin miner identity. What a miner needs to do is calculate some proofs out of the data that they are storing and submit that to the blockchain. So there is a process involved which is called sealing, and involves lots of kind of encoding and metadata addition to the raw data that a user has added onto the network as a service. And then the proofs that someone submits make sure that basically the miner is not misbehaving. The miner is behaving the way they should by storing the data, being online all the time, and making the data available to other users. So, you don't want to store your website with a miner, and then, when I go to click and access your website, the miner has decided to go offline. This is penalized by the protocol itself, because there is lots of, several different mechanisms for collateral and putting amounts of money, so that the miners are not incentivized to disconnect or do any other thing. Now, yeah, in a 30-second thing, this is it. The proofs make sure that the miner is the one that they said in the beginning they are, and the data are the data is the same as well. So if you stored your website, this is still your website being stored there and not some random garbage data.
Awesome. And for those interested, albeit it's right at the end, the mining event is on the 21st of September. So it's coming up.
I can certainly send lots of pointers later where you can find out about how all of that works in any level of detail you want. But I'm sure the final presentation is going to be much more enlightening.
Fantastic. Next question. What is it like working at a big decentralized organization like Protocol Labs?
It's a great experience. It's, the interacting with the community is a great thing, and being involved in the active development of those protocols and networks is certainly very rewarding. I can certainly certify that. And yeah, it's a very nice working environment, lots of interaction with the community, with others, with both internal and external people. So it's really good.
Yeah, very good. How does IPFS compare to Arweave?
Right. Okay. They have. Okay. So I would say, okay, Arweave, I think, it compares both to IPFS and Filecoin. There are lots of details there, and I would have to take a longer kind of amount of time in order to go into the details. But there is, I believe there is online as well, some kind of technical comparison, let's put it this way. Now, the foundations are different, Arweave. I'm not sure that they're not building on content addressing directly, and therefore, some of the problems can be kind of migrate from Web 2 to Web 3. But I'd prefer to leave it to that.
Very good. Are you happy to take some more questions?
I am, yeah.
Very good.
Get another few minutes.
Does Netflix use IPFS? I think I saw that Flora has seen Netflix on that slide you showed about different people that used Filecoin. That I was very curious as well. What's going on there?
Right. So there has been a collaboration between Netflix and IPFS, where Netflix used some of the protocols of the IPFS stack in order as a supporting protocol for their backend processes. So they wanted to ship containers basically between different data centers and virtual machines that they are running, and they have been using IPFS a lot for that. In particular, they use BitSwap. So certainly I can relate to that. Maybe there has been more. I'm not aware, but certainly this is something. And there must be a blog post as well, which I can point to later.
Very good. Hello, Elio. I don't know if I'm going to get your question right here. Does Infura's IPFS node provide pub/sub communication as well? Do you know what that means?
I do, yeah. So Infura's gateways must be supporting pub/sub as well. I don't know to what extent they. I'm pretty sure. I haven't looked at the details. I won't lie, but certainly, if someone is using, building on IPFS and the protocol stack and have libp2p, then the main pub/sub functionality of libp2p should be there.
Very good. How do grants work within the Filecoin ecosystem?
How do
grants?
Grants, right. So there is, I'm not aware of the details of the Filecoin grants. I'm pretty sure that, I know that there are many grants with Filecoin, and I can point you to the right repository in GitHub and elsewhere where you can find out. On Filecoin research, on the research side, if that's what you're asking, then there is a whole RFP program that I believe there are some Filecoin grants available right now.
Very good. Do you think there'll be a winner takes all in the storage race?
Difficult to say. Yeah, that's really difficult to say. The way that protocols and kind of online communities evolve have shown traditionally that there is more than one player. Now, whether this is going to change or whether one of them is going to be much more dominant than the others, like it's impossible to know, to be honest.
Fair enough. Can we have offline transactions using IPFS in times when there is an internet shutdown in a country?
Yeah, so let me clarify a couple of things. So transactions, when we say transactions, we might mean like monetary transactions for Filecoin and like other like tokens, and we can have transactions as in, you know, like from the web browser interact with a server somewhere else. Now, IPFS has got all the components to work offline, and there are applications that build on top of the stack in order to make them work offline. So IPFS can perfectly work like and transfer content between devices that sit in the same room. Now, IPFS does not have a blockchain. Like some, you know, there are lots of questions along those lines, and there is this kind of misunderstanding that IPFS runs on a blockchain or uses a blockchain. It does not use a blockchain and is not based on a blockchain. So Filecoin is what uses blockchain. In fact, it's got its own blockchain.
Very good. Is IPFS capable of live streaming?
Yes, there are applications that do live streaming on top of IPFS.
Perfect. Someone else, are you hiring product owners? But I don't think that's probably your specialty here.
I'm pretty sure there are lots of openings at Protocol Labs right now, and product owners could be. I'm pretty sure I have heard about, you know, such roles being open.
Yes.
But I certainly can't remember the details. Yeah, it's not my space, as you said.
End of, I think we had lots of other questions, but I feel like they got covered by
Excellent.
that. Is there any other content you want to share, Yiannis?
Yes, so I'm going to start now with content addressing module.
Perfect.
Which is going to be up. Yeah, give me a second. Okay, there we go.
Beautiful.
So as I mentioned in the previous module, like some of these videos that you are seeing, well, those that you're seeing today and some that you're going to see in the next weeks are part of ResNetLab on tour. And some of them, so this is one of the very basic ones. We are going to have a content, we're going to talk about content addressing, which, as I mentioned, is a very basic concept that is like touches throughout the entire Web3 ecosystem. So the agenda for this module now, which is going to be about 20-25 minutes, is going to go as follows. We're going to not cover too much on the motivation because we've done that already in the previous in the introductory talk, and then we're going to dive deeper into chunking. What does it mean to link chunks in Merkle DAGs, and what does it mean to go from data to data structures by using IPLD? Finally, we're going to look into a CID that is used by IPFS and go like split it into parts just to see what are the different parts it is composed of. Now, as I mentioned earlier, location addressing is something that can do with some improvement, and therefore IPFS and many other protocols are building on content addressing. Now, some like other motivation, apart from what we have I have covered in the beginning, is that when we have location addressing, the URL that we're using in the web today can only point to a single copy of the content in a single location. If that copy disappears, then the link does not change automatically. And therefore, that's when we get lots of kind of 404 errors. It is also not possible for a user to validate the integrity of data they receive. So you're receiving something, some web page, and you have to trust the fact that this address is, this content is what you asked for. So you have to rely on someone else. Finally, as we said, there is no kind of request aggregation, which means that we have all this inefficient use of bandwidth and resources. Now, location, when we use location addressing, we ask one particular server for a piece of content, ignoring the fact that much of the same content can be stored in other places in the network, in other servers or computers. Instead, when we have content addressing, we can ask any host. We actually ask the entire network who has got the content that we're looking for, and then we can just choose the one that is closest to us in order to receive the content that we want. Again, the slide that I showed before, just as a recap, we go from today we go from one URL to one IP address, which is a specific location. What we want to go is to something like this, where we have IPFS : / and this is the hash of the content itself. Now, this is the hash and what the CID looks like. There are two versions of a CID. There is CID version 0 and there is CID version 1. Let me get the laser pointer. Great. I'm going to talk about what these are a little bit later on. But what is basically what you can keep as a message from now is that the CID is the hash of the content that we have, that you want to publish or request for. And why is this useful? You can have, with CIDs and content-based hashing, what you can have is that you can have immutable links, which enable deduplication, self-certification, and immutability. Deduplication means that identical data can be verified by the address itself, by the address of the content. Therefore, you don't need to store files twice, even if they, like in normal file systems, if a file is, has got different file name, then you are going to have to store the data twice. With content-based addressing, you just don't need that. You can also cache content. You can cache content in the network and serve it when you see a request coming in. You can have self-certification, which means that you don't need to rely to someone else to say, let me see, I lost the right screen. Okay, sorry about that. Okay, I hope we're all back. So we can have self-certification, which means that content is authenticated by the address. Because we have the hash of the content itself, this means that if the content changes, then the hash is also going to change. And finally, we have immutability. If the content, what I just mentioned, if the content changes, then the address is also going to change, and therefore, through that, we have integrity checking. Now, what this means in more detail and why it's important. Say you have this piece of data, and you apply a hash, the hash on the data, you get what is called the fingerprint. So the hash of the value, looks something like the CID that we have seen. Now you want to, and you publish this in the network. What you want to do next is that you want to send it to your friends in order for them to go and consume the content. What they're going to do is they're going to ask the network for this specific fingerprint, and the network is going to send them some data. Now, what they can do is that they can hash the data that they have received and produce the resulting hash. If they compare that to what they asked for in the network, what they asked for the network for, or with what you have sent them, then if those match, they can certainly say that the data that they have received has not been tampered with, has not been changed, that what they asked for is what they have received. If those two hashes don't match, then this is a signal that there has been some problem in the network. Someone has tried to mess about with the data and so on. So they can discard the data and ask for it all over from the beginning. This is very important property because it allows the user to have control over the data that they consume. If some of the data, as I just said, has changed, then the user does not need to rely on external certificate authority, the domain name system, some ISP, or even the provider of the data itself. Now, the components, like largely speaking, of IPFS are those four. And right now, we're going to cover the content addressing module. There is the content routing and discovery module, which is the one that my colleague Alfonso is going to join us and present after the end of this. And then there is content exchange and mutable names. All those, they are available online in the link of the ResNetLab on Tour program. I'm going to link you to it just after I stop presenting, so that you can consume the content again, you can watch it again, and there is much more than what we're going to discuss here today. So let's dive into it. We start with chunking, which is the most basic thing when we start talking about content addressing. And chunking, as I'm pretty sure you all know, is when we have a single piece of data, a file, and we chunk it down into smaller pieces. This has been done traditionally in IP networks as well, like in communication networks in general, and it's advantageous for a number of reasons. The first one of them is deduplication, which I briefly referred to. And this means that if we have this file split into all those chunks, what we end up finding out is that there are two identical pieces of content here. There are these green blocks. So this means that we can optimize our storage requirements because we don't need to store it twice. We can just keep one copy of them. You can think of that as the same file stored twice within a hard disk or within a folder, or some kind of white space that is exactly identical with something else inside a big data set. You can have piecewise transfer, so you can discard only the parts that have arrived in error, and by error you can, of course, we can check that through integrity checking, which is what I mentioned just previously. And you can discard all those parts and not the rest of the file that you have already received. Finally, you can have random access, which means that you can first of all request the content that has arrived in error, but also it can enable things like you don't, like, say there is a big YouTube video and you don't want to watch all of it again straight from you don't want to watch all of it from the beginning. You just want to straight jump into 30 minutes into the video. Now, this is a huge improvement for the network because it doesn't need to go and transfer all those bytes that you're not interested in. Now, let's go into how we go about building what is called the Merkle DAG. The Merkle DAG stands for Directed Acyclic Graph. And some of you, I'm sure you have heard about it before. It's similar to Merkle trees or hash trees, where you have a graph-like structure which starts from one root node and breaks down into other nodes in this graph. Now, every chunk is represented as a particular node. The hash of the chunk is the address of the node. So whatever data is included in there is the address of this specific part of the kind of tree graph. And the address of every link is embedded into the parent link. So when you have the root node, you can know what are the children of this root node, and then going further down to the second level, you can know what are the children of that node as you go further down the tree. Now, what is not possible with Merkle trees, but you can do with a Merkle DAG, is that it's not possible to have one node in the Merkle tree cannot have multiple parents. Now, this is possible in Merkle DAGs, and it's very important because it allows for us to use deduplication, which is a major driver, as I mentioned in the previous slides, because you can optimize bandwidth, you can optimize storage, and you can do several other nice, have several other nice properties. So let's look into this with an example. Here you have a Merkle tree where you have the same file as we had before. We have each one of them has got its own hash. And when you want to chunk it down, of course, you have some kind of chunker size. And these starts well, in this case, is from 0 to 100 bytes, let's say. Every chunk has got its own address. This is what is also you're going to see in the IPFS ecosystem and community as the UnixFS, the Unix file system. UnixFS includes lots of those parameters to say how big the chunk can be and so on. Now, what we want to do with the Merkle DAG, and that's why it's used by IPFS, is to say that, look, this block here, this content block here is the same, and therefore I don't want two different identifiers for it. Instead, I just want one. I want to have the piece 1 and have both of the parent links pointing to this particular content object. This provides all the benefits of deduplication and so on that we mentioned before. And then the root is built out of those, and we finally have the entirety of the Merkle DAG for a particular file. Now, I strongly encourage you to visit dag.ipfs.io, where you can upload your own file and you can play with different chunk sizes and different even chunking algorithms, and have different types of trees where the file that you upload is actually going to be visualized as a Merkle DAG. So let's now go from data to data structures, and this is done with IPLD. We now have the data, we have chunked it in like in different pieces, we have built the Merkle DAG, and what we want to do is we want to be able to think of this graph as a tree of folders in the file system and be able to access files from different file systems, data structures, databases individually. So if we have a file that is stored in a different database, we want to be able to have the hash of the file and be able to go and directly access this part of the IPLD graph so that we retrieve the data that we want. This is done with IPLD. It's a very nice and very well thought through project. There is a separate module on the ResNetLab on Tour website, which with a very nice description of all of the details. And there is going to be a specific, I can't remember if it's the 4th or 5th or 6th week of this program, which is also going to dive into IPLD. It's a very important set of rules and principles that altogether, become the data model behind Web3 protocols. So from going from location addressing to content-based addressing, what we can see is that instead of having one URL that points to one specific address, we want to go to the hash, and we want to have the hash of the content and ask the network for whoever else has got this content. You don't need to, have only one host to serve this file, but you can have anyone with the file that can serve this to the requestors. And IPLD can do just that and lets you traverse through different data types of content linked data. Now, the final point, let's go and look what does a CAD look like and what are the components. As I said, these are two different versions of a CAD version 0 and version 1. Both of them are used in IPFS today and will continue to be used. And we have the benefits, as I mentioned, are self-certification, immutability, and deduplication. Now let's get the latest version of a CAD, which is a little bit more interesting as well, and try to see what is all this long and ugly alphanumeric string. These are the main parts of the long ugly thing. There is a multi-hash in there, there's a multi-codec, and there is a multi-base. The multi-hash is a self-describing hash digest, as we said in the beginning. Content is hashed using some hash function and produces a hash. So simplistically, that's what it is. A multi-codec, which is a preset number to uniquely identify a format or a protocol or a naming convention that you might want for your project or application. And when I talk about codec here, or multi-codec, or anything to do with codec, it has got absolutely nothing to do with video encodings. All these are about IPLD codecs, and should not in any way be confused with video encodings. And finally, there is a multi-base, which is the base encoding of the string itself. The format looks something like this. So at the very kind of deep down in the multi-hash, in the CID is the multi-hash, followed by the multi-codec, the CID version, and finally the base encoding. But let's look into this in a little bit more action. Here you can see the full list. If you go to this URL on GitHub, you're going to see the full list of multi-codecs that exist today in the Web3 ecosystem. So you can see that you can have things like IPv4. What happened here? Yes, like IPv4, which has got its own code and can be identified by that. Can be protocols like DCCP, which has got a different codec. And there are also serialization protocols like Protobuf and CBOR that have their own code as well and can be used under these schemes. Now, the multi-hash, which I mentioned, starts with, well, it is a hash digest, but includes some metadata, which make it very useful and very future-proof. So this is the hash digest length. So the length, how long is this digest? But it also includes the hash function. So if you have the same piece of data, but you apply different hash functions onto the data, the resulting outcome, the hashes that are going to come out of this, are going to be very different. So we don't want to be confused by the same data being used for, like, being hashed using different function. So the hash function itself can become a multi-codec and is a multi-codec out of this list and is included in the CID itself. So when someone gets a CID, they know what hash function to use in order to read the data. Finally, there is the multi-base, which simply, if it is a B, it's base 32. If it's Z, it's base 58, and so on. So let's look into it in more detail. We have this long, ugly thing. We start with, as we said, with the multi-base, which comes, if we go to this slide, comes first. And it's basically this first letter that we see here. When we see a B, we know that this is encoded using the corresponding, in this case, base 32 encoding. If it was Z, it would be something different, and so on. So what you know with this is how to interpret and read the rest of the CID, right? So you know what to do with it, and from that point on, after you apply the encoding that you have seen in the first letter, everything becomes a binary, which looks something like this. It's a long, like, list of zeros and ones, and that's what the encoding helps us do. Now, after that, we have the CID version, which you can see if it's a number, basically. If it's 1, then you know that it's CID version 1. If it's 0, then it's CID version 0. And if there are next versions of CIDs, like including more features or enabling someone to put more features for their specific application, can be another CID version, is going to be there. Now, then we go to the multi-codec. This helps us say it's one code out of the list that I mentioned before in that table, which tells us how to interpret the rest of the data. So it's in this case, the serialization protocol, which in this case is DAG protobuf and has got this specific code, and helps us see what is it that we're going to do, how are we going to deserialize the rest of the CID, and obviously the data that comes with it. Next comes another multi-codec, you guessed it, and in this case it's the hash function. So the hash that I mentioned before in this case is SHA-256, which is the default one used in IPFS and has got this codec, is shown here. And therefore, with this, you now know which hash function has been used has been applied to the data in order to come out with the CID that we are playing with. Then it's the length. And finally, after all these different steps, you have the actual content hash. So the formula-based CID is down here, and we start from the base, which is the first bit, the CID version that I mentioned, then the multi-codec, which helps us see what we're going to do with the data next, and the multi-hash, which is again is a set of different things, another multi-codec, the length, and the actual hash. Another very interesting website I strongly recommend you visiting is cid.ipfs.io, where if you put the CID, it's going to give you back something like this, which means that it breaks down the CID into all of its different parts. An interesting test that you can do is that you can put those two CIDs, and what you're going to see is that basically the digest of the content itself is going to be the same in both cases. It's just that the same content has been expressed as a CID version 0 or CID version 1, which has got all these different parts in it. Finally, one final point, which is a kind of misconception in some of the IPFS ecosystem, is that the CID is not the hash of the file bytes. It is actually the hash of the DAG representation of the file bytes. So when you're using IPFS and when you start playing with files, which is next week's lecture, you are going to first create the DAG, the directed acyclic graph, and then you're going to start getting the leaf nodes of the tree as we saw it, and compute the hash and build the tree out of that. Yes, and with this, I would like to start taking any questions that you have, and looking forward to all the rest of the program.
Awesome. Should we take them? Fine. Not too many. Let's take them. How do you stop malicious content being stored on IPFS? Kind of covered.
So depends what you mean by malicious content. The very short answer is that you cannot, because it's a permissionless network, as we said, and this is the case with many of the points that many of the platforms in the Web3 ecosystem. But if you want, like if you, for example, have build a specific project on top of IPFS, or build a company, then you can build your own AI-based or whatever-based algorithms to go and identify the malicious content.
Very good. Next question: what happens when the data gets too large for the nodes?
Gets too large for which nodes? Can we clarify that? For the nodes of the IPLD graph, there is more chunking. So when you have a file, it starts being split into chunks. Each chunk has got a specific size, and therefore, if you exceed this size, then you create another chunk. There could be that upper in the tree, you fall off the kind of limit there, where you do a different subtree in the IPLD graph.
Cool. A few general questions about what hashing is and Merkle trees and technical knowledge required to interact with what's going on with kind of IPFS and Filecoin, etc. Let's take the last.
If it's needed. If technical knowledge is needed, is that the question?
Yeah, just a general question. What level, if you're going to, I don't know, get involved with IPFS, Filecoin, Protocol Labs, what technical knowledge do you need? I guess, how much knowledge do you need? Is there a more kind of, superficial way of interacting with everything going on? What would you say here?
I think that if you go through this program that you're putting together, you're going to have everything.
Very good answer. Discuss the architecture of IPFS, says Rashid.
Sorry, can you repeat the architecture of IPFS?
The architecture of IPFS, could you talk a little bit to that?
So the architecture of IPFS. So we can, IPFS, the protocol architecture, let's put it this way, because there are several different kind of definitions of an architecture. The protocol level definition is that it starts with libp2p, which does lots of the magic of connecting different nodes in peers and exchanging data. IPFS comes on top of that and builds, has content addressing and the other different modules that are needed in order to be able to use it as a hypermedia protocol, if I can put it this way, which is an enhancement to HTTP. And then on top of that is Filecoin, which comes as an incentive layer. So in IPFS, you don't get reward if you join the system, you don't get reward if you serve content to other users and so on. Now, what you can do with Filecoin, of course, is that you add this incentive. So this comes on top as a layer. Now, as far as the architecture, like the network architecture goes, Alfonso is going to present content routing in the next module right now, is going to give a much better idea. But in one sentence, IPFS is a peer-to-peer network where you interact with other nodes directly by connecting to them or by using the distributed hash table, the IPFS DHT. So there are peers, they connect through either direct connections or through the DHT, and there are other supporting protocols that you can have other features such as mutable content and so on.
Okay, there's two more questions here. What hashing algorithm is used for the CID?
It's SHA-256 right now. As I mentioned, the important thing is that if that goes kind of out of fashion at some point, then you can just change it, and the CID is still going to be usable.
Very good. And last one: does IPFS reduce the need for a web application firewall? In other words, does it reduce risk of a DDoS or other threats?
It certainly does, because data is not stored. In one central server or data center. It's distributed all around, and therefore, it's much more difficult to find and kind of attack all those nodes. It's much more resilient because it's distributed. This doesn't mean that there are not other types of attacks that someone can do in a peer-to-peer network more in general, but certainly the kind of distributed and decentralized nature makes this much more resilient by default.
Awesome. Yiannis, thank you very much for that. For the first, well, the 2/3 part of this event. That was really awesome. Thank you.
It's been a pleasure, and I really enjoyed it. Thanks for all the questions. Alfonso is going to talk about a very central part of the IPFS network, which is the content discovery and content routing. So yeah, I highly recommend you stick around. Have fun through the rest of the 12 weeks and not even more. And I'll post all those links that I have promised.
Thank you very much, Yiannis. And Yiannis, he's actually on holiday at the moment, so we're especially appreciative for the time he spared with us this evening. So thank you very much.
Excellent. Thank you, guys.
Thanks. Right, Alfonso, good to have you with us to deliver the last module of today's event. Good to have you with us. Over to you. Please tell us more.
Thank you very much. I'm really happy to be here. So my name is Alfonso. I'm a research engineer at Protocol Labs. I work with Yiannis. And what I'm going to talk about is content routing. I will try to give you a better overview of what is the architecture of IPFS and how to fetch content from the IPFS network. This is the agenda that I'm going to follow in this presentation. First, brief introduction to understand something that Yiannis already described briefly, which is the difference between location addressing and content addressing, but from a content routing point of view. And we're going to see what challenges we face when trying to do content routing in peer-to-peer networks. We're going to then see the content routing architecture in IPFS, and we're going to see the different implementations that we have in place for this content routing interface, which is the interface that helps us find peers and content in the network. So what we're used to right now in the actual internet, in the actual architecture of the internet, is to find content through its specific location. So usually when we want to find certain file in the network, what we do is to go to a centrally governed system like DNS system. We ask for the specific location and the address of the server where the file is stored. We get this address and we fetch the file from the actual server. This is not the case for content addressing networks like IPFS. In this case, we don't have a centrally governed system to help us find where the content is, and we identify content through a unique ID, as Yiannis already described. So what we do to find content in content addressing networks and in IPFS is that we send a request for a unique ID for the content, and we start getting responses from different peers in the network saying if they are storing that content or not. At one point, we can choose one of these peers and request the actual download of the content. We see the difference here is in the way we fetch content and we find content in the network. And the main challenge that we have in peer-to-peer networks and in content routing systems for peer-to-peer network is that we don't have this central entity that we have currently with DNS, for instance, to orchestrate the storage and discovery of content. But not only this, like we don't know how to find where content is, but also we don't have a central directory to find how to reach every peer in the network. So we don't have a way of finding out like what peers are connected to the network and how to do it in a centralized way and without decentralized protocols. But also like in peer-to-peer networks, we have what we call high node churn. So we have a lot of nodes in the network that are continuously joining and leaving the network. And we have to face all of these challenges with thousands of peers and millions of content. So we'll see that with our content routing protocols, what we're trying to do is to prevent, like tackle all of these challenges in the discovery of peers in the network, in finding peers, finding the peers that are storing the content in the network, contacting those peers, so finding ways and finding the contact information for these peers in the network and doing it in a scalable way. And this is basically what we're gonna discuss throughout all of these model. This is, I'm going to mainly talk about the content discovery and routing system in IPFS, which is the one that is responsible for finding what peers are connected to the network, the content information for these peers, and find out who's storing what in the network. Then in the, as Yiannis mentioned, in the content exchange is where we actually discuss and describe how the content, once we know where it is stored, how we exchange the content between the different peers. And really briefly, our content routing interface has three simple operations. First, a provide operation, which is used to announce content in the network. Then a resolve operation, which is used to find out what peers in the network are storing the content. And then the fetch operation, which is the one that we use to explicitly download the content. And this is mainly managed by Bitswap, which is our main content exchange protocol. According to the content routing system that we're using, we may need to use additional schemes in order to find out the contact information for a peer. And we call these schemes peer routing. This is the case, for instance, of the DHT. That is something that we will describe in a moment. For the DHT, we use the DHT as a directory, as a distributed directory in order to find content in the network and who's storing it. But also, once we find out who's storing that content, we need to find the contact information for that peer. And this finding out the contact information for that peer is what we call peer routing. And right now, this content routing interface, I mean, the protocols that we use in IPFS and that implement this content routing interface are a DHT-based protocol, which is an implementation of the Cadimlia DHT, and gossip-based protocols like BitSwap, which does some kind of content routing with its neighbors, and PubSub algorithms that can be used to discover content. But this content routing interface could implement any other kind of protocol. We could use, I mean, we could even implement an DNS discovery over this content routing interface so that it could be used in IPFS, but it's not currently in place. And the design goals that we have to bear in mind in order to implement our own protocol that implements this content routing interface to find content in the IPFS network is that it should be reliable. So we should have a way of finding any content in the network, and it should ideally be scalable and fast so that the performance of the protocol is not harmed by the scale of the network. And finally, like, you have to bear in mind that in peer-to-peer networks, we have node churn and Sybil attacks. So we have a lot of nodes. Nodes can join and leave, and nodes may create new identities and change identities. So these protocols should bear in mind this when they are designed. And quick detour before we explain how content routing actually works. What is a peer in the network? So a peer in the IPFS network is a device that has a unique ID in the peer-to-peer network namespace. These devices will be running different protocols and interacting with other peers that are running services and protocols that we want to use, leverage, or interact with. Ideally, in the IPFS network, peers need to be discoverable. So we should have a way of finding out a peer which is connected to the network. And as we'll see in a moment, this is done through the DHT. And also they should be routable and reachable. So we should have a way of contacting them and establishing connections with them. The way in which we do this is through what we call multi-addresses. And these multi-addresses in the end is the string that specifies, like a URL that specifies all of the protocols and the endpoints that this peer has open and is running to interact with other peers. And I briefly mentioned that every peer has a unique ID. Whenever we switch on our peers in the network, the first thing that we do is to generate an asymmetric key in order to, and that is used for two purposes. First, it is used to create this unique identity that will identify my peer. So we use the public key of this cryptographic keeper in order to infer the ID of my peer. And also it is used to establish security channels, because the communication between every two peers in the IPFS network is done using a secure channel. And the way in which we establish this secure channel, we negotiate the keys for this secure channel, is through this cryptographic keeper that identifies us. And right now, like the main way in which we find content and peers in the IPFS network, as I've said, is through a DHT, through the IPFS DHT. And for those of you that are not aware of DHTs and how they work, in the end, like a DHT is a two-column table that we collaboratively store between all of the peers in the network. And the way in which we know if we are responsible for storing the value for a certain key is through what we call the distance. So we check if we are close to that key ID. So if our peer ID is near that key ID that we need to store, and if we are the closest peer for this key ID, it means that we are the ones responsible for storing this content. And this DHT is used for several purposes in the IPFS network. First, for peer routing. So in this case, what we're storing as the key in the DHT is the peer ID for a peer, and then as a value, what we store is what the contact information for that peer, the multi-address that I mentioned before. So if we want to find out the contact information for a peer, we just have to do a lookup in the DHT for the peer ID, so for this key and the peer ID of certain peer. We also use the DHT for content discoveries. In this case, what we're storing as a key is the CID of the content of the specific block that a peer is storing, and then as the value, the peer that is storing that content. We'll see in a moment how this content discovery works. And also, we use the DHT for IPNS records. For IPNS records, I'm not gonna describe them in detail. If you wanna learn a bit more about IPNS records, go to the mutable content module that explains it in detail. And the specific implementation of the DHT that we use in IPFS is the Cadimlia DHT. actually, it's an adaptation of the Cadimlia DHT that uses a 256 bits address space. So we use a SHA-256 to move from peer ID, for instance, to the address space of the DHT. So whenever we want to find the key, like for instance, some content in the network with certain CID, the first thing that we will have to do is to do a hash or a SHA-256 of this key in order to move from CID to the address space in the DHT. And then with this information, we can compute the distance that I mentioned. And the way in which we compute distance is really straightforward. We take the key in this DHT address space and we XOR it with with any other value, like the peer ID with the value ID or whatever, to two keys in the DHT for which I want to compare the distance. And the routing table, the routing tables for DHT peers that are represented in a tree as the one that we can see here. So our local routing tables, we have this structure of a binary tree. And whenever we want to find out who's storing, like for instance, we want to perform a lookup in the DHT for a key that has a prefix 101, what we do is that the first thing that we do is check our local routing tables, and we go 101 to this bucket, because these circles that you see here, we call them buckets or K buckets, and what they store is a list of peers that share the same prefix. So here we see that these different buckets, what they're storing is a list of peers recently seen that share the same prefix. If we want to find some content that has a prefix 101, what we do is check first our routing tables, see the peers we have in the K bucket, in our K bucket for that prefix, so 101. We send them a request, and if they have the content that we're looking for, they will send it back to you. So if they have the value for the key that we're looking for, they will send it back to us. And if not, what they will send back is a list of peers, of closest peers that they have in their own routing table. So in this way, we will be able to be jumping from one peer to the next one until we find the closest peer that is storing the key that we're looking for. So this is basically how the DHT works, and I'm going to explain now how we use it in IPFS, because I told you that the first operation that we have in the content routing interface is the provide operation. That is the one that we use to announce content in the DHT. If we want to announce that we are storing a block with a CID1, the first thing that we need to do is what I mentioned, like do the hash SHA-256 of CID1 in order to go to the address space of the DHT. Something that is worth noting is that content in the IPFS network is not replicated or uploaded to any external server. So the content stays local, and what we put in the network, so what we put in the DHT is just a pointer to our own peer, to let everyone know that that CID is a pointer from CID to peer ID, so that CID is stored by me. So if I want to announce certain content in the network, as I've said, like we take the CID, we hash it with a SHA-256 in order to move to the DHT address space. And what we do is find the 20 closest peers to this key in order to put in them this provider record, which is this pointer to my peer ID. So I do a lookup in the DHT to find the 20 closest peers to the key in the address space, and I put this pointer to my own machine in them. The problem is that, as I've said, like peers are continuously joining and leaving the network, so we have churn and we have to accommodate this churn. The way in which we accommodate this churn is by republishing this provided record periodically. So we have to accommodate two types of churn. The scenario in which I am the one leaving the network, so the pointer ends up pointing to a peer that is no longer in the network, so the content is not in the network. And in this case, what we add is an expiration to the provider record. So if at one point one peer doesn't republish, this provider record expires and this pointer expires, and it points to, it can't be found from there on in the network. But also, the provider of the content can disappear, but also the ones that the 20 nodes that are storing these pointers can also disappear from the network, and we wouldn't have pointers to the content. So to accommodate for this, like there's a periodic 12-hour republishing of provider records, so that we find the new 20 closest peers and put the provider record again in them, so this pointer again in them, so that others are able to find this pointer to myself, which I'm the one storing that content. And at this point, like once we have this provider record in the system, anyone can start fetching the content from the network. When we provide content to the network, we become permanent providers for that content. But if someone gets that content from the network, what they do is that they become temporary providers for the content. So it means that they won't put this pointer in the 20 closest peers, but so this pointer won't point to them, but they will still provide to others the content if someone asks for it. And content that is stored in a temporary provider is garbage collected every hour. So if at one point our IPFS client reaches the 90% of its total storage, that by default is 10 gigs, every hour there will be a garbage collection for all the temporary data for which we are not permanent providers. If at one point we want to become permanent providers for certain content, what we have to do is what we call pinning the content. And by pinning the content, what we're doing is fetching the content and updating this provider record, so this pointer, to also point to ourselves and not only to the original provider of that content. So this is how we announce data to the network. Then we have the getting content from the network, so the resolve operation. And how do we do this with the DHT? So we do kind of the same, we follow a really similar approach. The first thing that we do, we want to find content for CID1, we hash the CID in order to go to the DHT address space, and we start performing a lookup in the DHT in order to find the provider record. So what we do is find the 20 closest peers in order to see if any of them has this provider record that goes from CID to peer ID of the peer that is storing that content. Once I get the provider records, once I see the provider, I get the provider record, I get a list of peer IDs that are storing the block for the CID that I'm looking for. At this point, I look my routing tables and I may not have the contact information for these peers. If this is the case, we need to perform an additional lookup in the DHT in order to find the multi-address, so the contact information for the peers that are storing the content, so that I can establish a connection with them and request the download of the content. That's why we say that in IPFS, we use a multi-round iterative lookup in order to find content in the network. And another thing that is worth noting in IPFS is that since recent upgrades of the protocol, we don't use a single DHT, but we use two DHT, a public one and a private one, because we were facing the problem where a lot of the peers that were providing content were behind NAT. So whenever we performed the lookup in the DHT, we ended up finding peers that are behind NAT and for which we couldn't establish connections to them. In order to prevent this performance overhead of like timing out because we were trying to establish connections with peers behind a NAT, what we built is a public DHT and a private DHT. In the public DHT, we only include peers that are publicly reachable from a public network, and then for the private DHT we include peers that are in our same network, so that whenever we have to do a lookup, we do a parallel lookup in the public DHT and the private DHT to see if we are able to find the content. And of course the DHT has its pros and cons. As a pro, like it is fault tolerant, it's really resistant to churn, it finds peers and content in the network with 100% probability as long as the peer is reachable, and it ensures the freshness of the routing information. The problem is that when we scale, so when the scale of the network is large and we have a large number of peers in the network, the lookup operation may be slow and performance may be impacted. And also there's another issue with DHTs, which is that we're building an overlay over the underlying transport network. So this means that when we say that we're one hop away in the DHT, so that we're close in the DHT, it doesn't mean that we're close in the underlying network. So a single hop in the DHT may be several hubs in the underlying network. And this is actually an open problem and an active line of research that we're exploring, which is how to make the overlay made by the DHT as similar as possible as the underlying network, so that one hub in the DHT is actually one hub in the transport network. And here I just wanted to share a few defaults of the values we use for the DHT in IPFS. You see that our K buckets, so the number of peers that we keep in our routing tables, are 20 in each of these buckets that I showed. Alpha, which is the number of closest peers that we query in order to find content, is 10. If when we perform this lookup, we receive 3 successful requests at the same time, we don't do the full lookup, so we don't wait for the rest of the peers to answer, because we consider this response as good. And the K bucket refresh interval, so the interval in which we refresh our own routing tables and information in our K buckets, is 10 minutes. And finally, like something that I mentioned, the republish interval that we use is 12 hours, because we need to accommodate for churn, and also the provider records expire every 24 hours. And when we are temporary providers for certain content, every hour we will garbage collect the temporary content that we are not permanently providing. And this is the main way in which we can find content and use content and implement the content routing interface in the IPFS network. We have alternative ways that we can use to find content using, for instance, a gossip-based approach. In a gossip-based approach, what we do is talk to our neighbors and talk to other peers in the network in order to find out where content may be. A good example of this is Bitswap. Bitswap, we're not going to talk today about Bitswap, but it's the main content exchange protocol in IPFS, and it talks to its neighbors in order to find out content before having to perform a lookup in the DHT. The same way that we can implement, like right now, we can only use this gossip-based approach or DHT-based approach, but as I mentioned, like the idea of having a content routing interface is that anyone could come up with their own content routing protocol, design it, and implement this content routing interface. And from there on, IPFS will be able to leverage it in order to find content in the network. And in order to wrap up this model, I'm just going to give you a quick walkthrough of everything that we've seen and how fetching content from the IPFS network looks like. So the first thing that we will get is the same way we get a URL in the internet, we will get a CID out of bound to find content in the network. When we say get CID in our and trigger that action in our IPFS client, the first one that comes into action is the Bitswap protocol, because the Bitswap protocol, as I mentioned, does this gossip-based content routing and asks all of its neighbors in case any of them has the content we're looking for. If none of them has it, what we have to do is to perform a lookup in the DHT. So we perform this first lookup in the DHT where we try to find for the CID who is the peer ID. We want to find the provider record that for a CID points to the peer ID that is storing that content. We get the provider record, we get a list of peer IDs that are storing that content for the CID I'm looking for. And the next thing that we have to do is, if we don't have the multi-address for any of the peers in that list, we need to perform an additional lookup in order to find the contact information and the multi-address for these peers. We get this contact information and we establish a connection with the providers for that content. And we use Bitswap to request the actual exchange of the content. And just to remind you, whenever we fetch content from the IPFS network, we become temporary providers until the data is garbage collected from our local IPFS client. And that's all for content routing in IPFS. If there are any questions.
Awesome. Well, thank you very much, Alfonso. Has anyone got any questions? No, lots of just great presentation. Sorry, I'm going to close my window. There seems to be a helicopter outside my room at this exact moment. There we go. No, I think that's everything. Someone said you should do rap battle. I think it's because you got through a lot of them very quickly.
And I move my hands a lot. Hope you enjoy that.
That was really good, Alfonso. Thank you very much. Oh, someone asked a question. Can you please comment on how slow will it become when n/w scale?
Right, so we could go, actually, in the slides, there's the math behind it. Actually, it's logarithmically according to the number of nodes. So it's, I can share the math. I mean, the more nodes you have, it will increase logarithmically with the number of nodes. It's complexity. I don't know if you, it's this way. So it depends on the specific implementation, the latency that you have in the network, but like theoretically, that is how it will increase. So if you right now spend like 1 second for each lookup, and you add 1,000 more nodes, you will have an order of 1,024, you will have an order of plus 10 in the performance overhead.
Very good. Also, is it practical if this slows down?
So that's why we have several ways of finding content, and that's why we are trying to perform improvements. So there are tricks in order to make the DHT faster. For instance, you could, instead of like trying to perform a lookup from scratch, you can cache certain information in your local routing table. You could even like use the gossip-based approach to find content, and then we are not explaining, and it's a pity, we are not explaining Bitswap, but what Bitswap does is that just like have the penalty of going to the DHT in the first block and then fetch the rest of the blocks after establishing a connection. So we have ways of like accommodating a large scale network and the performance overhead of having to perform lookups.
Awesome. Thank you very much. Any other questions for Alfonso or Yiannis at all? Awesome. Well, Alfonso and Yiannis, thank you so much for your time this evening. This will go, just for those of you that are here, this will go onto YouTube and onto Medium with the slides. There's also a lot of associated content which will go up in that Medium post, so you can learn in your own time and go back. And we got through quite a lot of content today, almost 2 hours worth, so you can go back and digest and ask questions. And Yiannis has mentioned there's a tutorial on Bitswap specifically as part of the ResNetLab on Tour program. Just last thing from me, just to flag this, obviously this program will be running, at least the education part will be running every Tuesday, and the next event is on Tuesday the 13th of July, so a week today, at 5:30 once again, which is an introduction to IPFS. So it's the second event. So please do join us for that. And for all the events, these are on the websites, on various websites. Let me put it online now. This is the main one if you want to go and check out what's coming up, and make sure you're signed up for those. And do make sure you'll sign up to the Discord as well. That is just a place where we again post lots of information, and a chance if you've got any questions during the program for you just to ask, really. And I'll stick that on the chat too. Well, look, thank you very much to Yiannis and Alfonso for such an awesome presentation, such awesome presentations, and so much depth and insight, and answering the questions. I certainly learnt a lot, and I'm sure everyone did as well. So thank you both very much for your respective time this evening.
Thank you, Anthony, and everyone. Great event.
Awesome, great. Well, the slides in the video will go up tomorrow, everyone. Thank you very much for joining us. We're looking forward to the future iterations. And in the meantime, have a good evening and see you all very soon. Thanks all.